This is Science Max, Experiments at Large. Science Max!
Oh, hi, Science Maximites. Have you ever been eating pasta and wondered, what could I build with this? Could I build something that could hold an impressive amount of weight? Well, I have, and that's what we're gonna do today on Science Max Experiments at Large. But we're not gonna use cooked pasta because it's too delicious. We're gonna use uncooked pasta, which is less delicious, but it's great for building. We're gonna make a pasta bridge. Here's how you do it. First, you wanna start with a plan. And then you wanna take your pasta, I'm saying pasta, but of course spaghetti is usually the best thing to use, and lay it out on your plan. The reason you have a plan is so that you can make sure all of the spaghetti is exactly the right length. Lay it out on your plan, perfectly aligned like that. There. And now it's time to glue it all together. Now you can use white glue, but it takes a long time. So I suggest a hot glue gun, but make sure you get an adult's permission before you use one of these, okay? So you take your plan, you lay it out, you glue it up. Don't glue it on the paper because that will be bad. And you will end up with your truss, and it looks just like this. Now remember, you want two sides because those are the sides of your bridge. And as you can see, I've used several strands of pasta because that'll make it a little bit stronger. Once you have your trusses, it's time for the next part of the plan. This is the roadway, and it works the same way. Lay out your pasta, glue it up, and bam, there it is. Now, you put your trusses on your roadway, and you glue them all together, and you also want to put some struts along the top here, probably, to keep it nice and rigid. In the end, you will end up with a fantastic looking pasta bridge. Pretty good, huh? No, pasta bridge. No other bridge could claim to be 100% pasta. Minus the glue, 99.8% pasta, 0.2% glue.
I say there, Captain. Set sail. Set sail for the land of pasta bridges.
Now, if that was pretty fast for you, don't worry, all the instructions are gonna be on our website. Now, a bridge isn't a bridge unless it spans a gap, because that's what bridges are for. So you put your pasta bridge up there, across the books like that, and then you can see just how much weight the bridge holds. It's pretty impressive. If you build it right, even something as flimsy and as delicate as pasta can hold quite a bit of weight. I like to use big, heavy blocks and put them in the middle where there is no support from the books whatsoever, and just keep adding heavy things and see how much weight the bridge will hold before it breaks. How much will it hold? Well, I'm not gonna tell you. That's where you get to be Science Maximites and find out for yourselves. And now, we're gonna max it out. Today on, oh, my pasta. Today on Science Max Experiments at Large, we're gonna be looking at how fragile things can become strong if you build them right. We're also gonna be maxing out the pasta bridge experiment to see if we can make one that's strong enough to hold me. You think we can do it? I know I have no idea, but I'm going to the Center for Skills Development and Training to find out. Oh, hey, Kyle.
Phil.
How you doing?
Great, thanks.
Awesome. This is Kyle. He's got a master's in civil engineering. Did you want some pasta?
I'm good.
I can go back and get some more.
Really, I'm good.
Okay. So what does a civil engineer do?
Well, a civil engineer builds the world around us. Talk about our homes, keeping us warm in the winter, our roads, hey, even our bridges.
Bridges, that's fantastic, because that's what I need your help with. I want to max out the pasta bridge.
Awesome.
I want to make one big enough that I can walk across it.
Okay, that's never been done before.
I know, right? You think we can do it?
We're gonna need a lot of help to do that.
We don't need help. All we need is a lot of pasta, which I have. Ha-ha!
Nice.
What do you say?
Yeah, let's give it a shot.
Okay, we'll give it a shot. Why don't we just take some to start, and then...
In order to max out our pasta bridge, the idea is to take many, many strands of pasta and just keep gluing them together so the long beams of pasta in our giant bridge is nothing but many, many regular-sized strands of pasta. Here's where we were after 20 minutes of gluing.
There, that's nice.
Yeah, I think this piece is done.
Okay, so how does it work? Is it strung? Whoa.
Well, let's give it a go, eh? Yeah, I think this will hold.
Great. So we just need to build a few more of these then, right?
Yeah, that's right.
How many more?
212 more.
212 of these.
More.
212, but it took us like 20 minutes to make this one.
Yeah.
Oh, well, I guess so. I mean, this is Science Max experiments at large. That's what we do. We just keep building, and, you know, I don't have any plans for the next while, so we can...
Phil.
Yep.
I think that there's a better way of doing this.
I would be delighted to know there's a better way. It'd be faster than this.
Much faster.
Sure, let's do it.
Awesome.
I'm just gonna put the pasta back in the bag because it'll
Phil,
get stale.
You don't have to do that.
No, but it'll get stale.
Phil, I'm gonna call in one of my friends. We're probably gonna need some more help with this.
Oh man, that's a great idea. Sorry, that's a great idea because
Yeah.
Because at least we could get your friend to help clean up.
Better sandcastles in 80 seconds.
Building sandcastles is fun, but you can't use dry sand because it doesn't stay up very well. You have to use wet sand. But even if you use wet sand, it doesn't hold a lot of weight. But if you use sand with the power of science, it does hold the weight. Dry sand, wet sand, science sand. Here's what's going on. Say these ping pong balls are grains of sand. When they're dry, they don't hold together very well. That's why you can't build a sandcastle out of dry sand. But if you get the sand wet a little bit, the grains of sand will hold together a little better because of the surface tension of the water. That's why it's easier to build a sandcastle with wet sand, but they still won't hold much weight. But if you add something that creates even more friction between the grains of sand, like say this sandpaper, it will hold the weight. So here's what you do. Take window screen and cut it into circles. Make sure you get an adult's permission first, okay? Deal? Put in a layer of sand, pack it down, and put in a circle of window screen. And a layer of sand, pack it down, circle of window screen. Then, you guessed it, layer of sand, pack it down, circle of window screen. The window screens are gonna add more friction between the grains of sand and will make your sandcastle strong. Strong with the power of science. And then, you can put lots of weight on it. And there you go, sand with the power of science. Ha ha! Okay, I had to max it out. Let's see how strong science sand really is. Huh? Ha 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 ha! Science!
Our pasta bridge was going to take a long time to build out of individual pieces. So we have a new plan.
Hey, Michaela.
Hey, Phil.
How you doing?
I'm great. How are you?
Good. This is Michaela. She's an undergrad in industrial engineering, right?
I am.
And you and Kyle have a new plan for how we can build our pasta bridge that's not gonna look like this.
Oh, man.
This is the best that Kyle and I could do with 20 minutes.
Okay, well, I have better.
Good, I'm glad. How are we gonna do it?
So, instead of that, we're gonna try something like this.
Oh, okay. This is sort of like a giant burrito kind of thing, right?
Yep,
But we're going to build the bridge out of this.
exactly.
We're gonna make it longer though?
Yep, we're gonna make it 8 feet long. We have this long pole, right?
Yep.
And we have sheets of this pasta. We're gonna put them on the diagonal,
Okay.
and we're gonna roll it, but we're gonna start from this corner, and we're gonna keep rolling.
And don't
all
forget
right?
to add water.
And we gotta add water.
I'll add the
'cause-
water.
Okay.
Adding water, just like this?
Yep. It helps the pasta to stick together. So as we're rolling, we're rolling, we're rolling. We're gonna keep doing this with a bunch more sheets so that it gets really, really long, like 8 feet long. And when we're finally done rolling, we gotta spray it with some varnish,
Yep.
and so it all holds together.
Great, and then it's gonna be about this thick
Yeah,
when we're finished with it.
exactly.
This is gonna be one of the parts of the deck of our bridge.
Great, so each one of these large pieces is gonna be like one single strand of pasta and the little bridge with it.
Yeah,
We need a lot of these.
a lot.
A lot.
Yeah.
Still, it's a lot faster than doing it piece by piece with just the spaghetti.
Oh.
Every time I hold it up, you make that noise.
Oh. Oh. Oh.
Awesome.
The shape of something makes a big difference in how strong it is. Get some toilet paper rolls and put them in a square, and then stack books on top of them. They can hold weight. Thing is, they can actually hold a lot more weight than you probably think. In fact, the amount of weight just paper in a tube can hold is really kind of impressive. Ha-ha! And now, let's max it out. Bill's weight on 2 toilet paper rolls. Nope. Bill's weight on 4 toilet paper rolls. Nope. Bill's weight on 6 toilet paper rolls. Nope. Bill's weight on 10 toilet paper rolls. Oh. Ha! Ha ha! Bill's weight can be supported by 10 toilet paper rolls. But what if Bill jumps? Ha 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 ha! Didn't really work.
Kyle and Michaela's plan is to use a long pole and sheets of uncooked pasta. We roll the pasta around the pole and spray it with a little varnish. We roll sheets and sheets of pasta along an 8-foot-long pole, making many layers of pasta. Then we wait for it to dry and remove the pole. What we have is an 8-foot-long hollow tube of pasta that becomes a single piece of the bridge. Then we attach a bunch of these pieces together and use more sheets of pasta to glue them into the shape we used for our small pasta bridge.
We're making our giant pasta bridge by wrapping sheets of pasta around and around the poles using the technique we just had, making a whole large pole out of many, many, many sheets of pasta rolled around each other. And we've made a giant truss. Look at this. This is great, guys.
It's looking pretty good.
Yeah. If I hit it, you think it'd stay together?
No, stop.
What?
This is pasta, not steel. It's only made to just hold you.
Kyle, what do you think are the chances that this is gonna hold me when we build it?
Something like 50-50?
Not bad. Michaela, what do you think?
I'm gonna hope for the best.
Hoping for the best. That's exactly the kind of gray area we like to work in at Science Max Experiments at Large. Experiments at Large, I don't know if anybody's even ever done this before.
Not to my knowledge.
I don't think so.
Which is why we have no idea if it's going to work. Okay, so one more of these, because these are the sides.
Yep.
Roadway, and then the top.
Yep.
Yep.
All right, let's do it.
While we're waiting, it's a good moment to point out one of the things that makes our bridge really strong. That is triangles. As you can see, the truss, or the side of our bridge, is really just 3 big triangles. Triangles are very strong shapes to build with, and they work great in bridges. Now it's time for Science So Simple, a caveman could do it. This is a caveman. Today we're going to teach this caveman how to build a strong structure. Here are some boxes. Go on and build a shelter, and I'll come back and see how it worked out. No, that's not right. You need to build walls by stacking boxes on top of each other. That's how you build. Understand?
Oh, yeah.
I'll come back later and see how it worked out.
Yeah.
Uh-oh. Does that look right to you?
Yeah.
Look at those boxes. They're stacked on top of each other. But if they are in tall stacks, what would happen if you push on the wall? You see? Walls don't stay up if you build like that. Let's try again. I'll help you this time. First, lay out the foundation, where your wall should go. Good. Now let's make the second level. No, don't put it right on top. You need to stack in between. That's how you make a strong wall. Okay, I'll come back later. Nice work. Why don't you give it a try? Looks strong, but you forgot a box. Join us next time when we talk about how to make a door.
Building a door in a wall is hard because how do you make a big gaping hole in your wall without your wall falling over? Well, people have come up with lots of ways to put doors and windows in walls made of stone blocks over the centuries. And you can do this at home with books like I'm doing or with building blocks. Just go up until you're happy with the height and then stack each next layer a little closer to the middle until the final layer touches just like this. And then you take a big heavy book and you drop it right on top. And it's pretty stable and you've just made a doorway. It works even better if it's part of a wall because you want extra weight on the outside of these books here. So of course, I had to build one that was part of a whole wall. This is the same corbelled arch built out of little building blocks. And as you can see, I went closer and closer together until it meets at the top, and it is very strong. Whoa. Ha-ha! Now, let's max it out.
The kind of arch we're building is a corbelled arch. And the Science Max build team and I are using pieces of wood cut to different lengths.
How high can it go? We can use my head to, no, okay, wait.
It takes a while to get together, but once it's done, it looks just like the kinds of doorways stone buildings had in ancient times.
Ta-da! There you go, a maxed out corbelled arch. We went straight up until we got to these layers, and they got a little bit closer and closer to the middle until the last piece is one big solid piece. And if we built this right, it should be strong enough to hold me up. Yeah! Science! Woo-hoo! Well, it held me up for a minute, didn't it?
We rolled our pasta and constructed one truss. Now we've made a lot more rolls of pasta and connected them all together to make a second truss and a roadway, as well as the cross braces on top. And when we get it all together, we end up with...
Whoa! Pasta bridge!
Pasta bridge!
We did it! We built it. We have no idea how long it will stay up. But it's up. It's doing its bridge thing for now, anyway. I am very excited because, as far as we know, I'm the only one to try to cross a bridge made out of pasta. What do you guys think?
I think I don't want you to be the last person to cross a pasta bridge.
You're absolutely right. But I'm gonna do it. I think we're ready. Yeah?
Yeah.
Okay. Here we go.
Ah!
Oh no! That doesn't bode well for our pasta bridge. What happened here, Kyle?
You put all your weight in the middle of the joist. It snapped.
If only there was a way to distribute your weight. Maybe if you crawled?
Do like the military style kind of.
Oh, right, so that I'm putting my weight on more than one spot.
Yeah, yeah.
Exactly.
Oh, wait a minute. That gives me an idea. You guys stay right there. I know what to do. I know what to do. I know what to do.
You're coming back, right?
skis distribute your weight over a large area so you don't sink in the snow. That's what skis do, which is perfect for the pasta bridge.
Come on.
Okay, here
Come
we go.
on.
Carefully.
Uh-huh. Is it working?
It's working.
I hear some cracking.
This might do it.
Uh-huh.
Try to spread your legs apart.
Spreading my
Distribute
legs
your weight.
apart.
Distribute your weight.
Distributing my weight. It's swaying a lot.
Oh man.
Oh. Whoa. Crossing the pasta bridge. Woo, high fives. There you go. Science Max, experiments at large, pasta bridge, skis. What more could you want? Maybe a pasta chairlift of some sort.
Greetings, Science Maximites. I have a question for you. Have you ever wanted superpowers? Like super strength? Well, today on Science Max Experiments at Large, I'm gonna give you and myself super strength using the power of science. But we're gonna do things a little differently today. You see, well, the portal hasn't been working perfectly since I built it. But I ordered a new particle impulse controller, and all I have to do is get it back to the lab. Perfect timing. It looks like the portal is broken. Okay, well, no problem.
Okay, I'm here. Wow.
That's perfect. One particle impulse controller for you.
All right, thanks very much.
Problem.
Appreciate it.
Enjoy.
Thank you. Well, my very own particle impulse controller, okay. That's as heavy as I thought it was gonna be. All right, Science Maximites, this episode of Science Max Experiments at Large is gonna be a little different because today I'm not gonna have an expert come and help me because I'm gonna move that giant, heavy particle impulse controller all the way across the parking lot and all the way up that loading ramp by myself with nobody's help. How am I gonna move a giant, heavy machine all that way if I can barely even budget? Well, I'm gonna give myself superpowers, super strength with the power of simple machines. And the first machine we're gonna start with is the lever, which I guess I should go back to the lab to tell you about.
All right, Sal, I'll see you next time. Oh, hey, how you doing? Let me guess, you got some work to do and you need it done easy, right? I mean, look at this book. I mean, you could pick it up, but what, are you gonna be some sort of book picker-upper person now? Is that all you're gonna do? Is that gonna be your life, just picking up books left, right, and center? No, you're smarter than that. You know what you need? A lever, like this. Now, I know what you're thinking. I know you're thinking, hey, this is just a plank. You're right, that's because you're smart. A plank can be a lever. All you need is two sides and a place for it to pivot. A fulcrum. It can be anything. Look at this. Bam! Now it's pivoting. I put the book on this side, and then I push down on that side. I'm doing work easy. Hey, look at me doing this work over here. If I want to do more work, I could move the fulcrum a little bit further over. Now I do lots of work, but I lift the book a lot further. Look at that. Whoa! Wow! Whoa! Yeah! Huh? What do you say? What do you say? Huh? Huh? You don't like this lever? Don't worry. Hold on. I got another one for you here. Hey, take this stick. All you need is two ends and a place for it to pivot. Like this. Bam! Now, it's a lever. This side goes down, that side goes up. Down, up. It's a lever. It's a lever. You want to make a catapult? Use a spoon. The place where the spoon pivots is the fulcrum. And now, it's a lever. It's a lever. It's a lever. Look at this lamp. Now, it's a lever. Scissors, two levers. Your forearm, it's a lever, two ends, and the fulcrum where it pivots, yeah, the fulcrum can be at one end. Crazy. This fish, you guessed it, now it's a lever. And now you know your levers. Okay, where were we? Oh yeah, levers. So you can use levers to become much stronger, or at least lift something you couldn't normally lift. Levers are simple machines and they work like this. Levers are just a long rod or a stick or pole or a piece of wood like I've got here, and something for them to pivot on, a fulcrum. Now let's say you have something heavy, like this book. Sure, I can lift it, but what if I told you I can lift this heavy book with this book? Now, if the fulcrum is in the middle, like a seesaw, you can tell that book is much heavier than the other book. But watch what happens when I move the fulcrum. Huh? It's like magic, but it's not magic, it's science. Whoa. It's because the small weight is moving a long distance and the heavy weight is moving a short distance. Small weight, long distance, heavy weight, short distance. So everything balances out. But here's where it gets interesting. The longer your lever, the more weight you can lift. These are two heavy cinder blocks. There's the fulcrum, and here is a very long lever with which I'm going to lift those cinder blocks with this book. Ha-ha! And there you have it, levers. Now, back to the particle impulse controller. Oh, right. Ha 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 ha! Lever! Here we go. I got my giant lever. The bigger the lever is, the easier it is to do the work. I need a fulcrum. Just about anything will do for a fulcrum. And put that there. Now the hardest part is getting it on the lever. Okay. All right, hardest part is over. Get the lever up on the fulcrum. And, oh, look at this. No problem, one finger lifting. It suddenly became very easy for me to move this. I guess I need to do more than just lift it though, huh? Because I have to move it all the way. Oh, rollers! Come on, back to the lab. Okay, rollers. Rollers are like wheels, except they're not attached to anything. In ancient times, they used to move giant, heavy blocks of stone using rollers. We can demonstrate using a book. Now get a book, put it on a table, and try to move it across the table. You'll see that it's very difficult. I can't move this book across the table. I can't. Okay, it's not really that hard, but still, it takes effort. But if we get some rollers, I like to use pencil crayons and not pencils, and here's why. Take a closer look. You see, pencils aren't round. They're hexagonal. They have 6 sides, whereas pencil crayons are round. And of course, if you want something to roll, you want something round. So get a bunch of pencil crayons and put them on the table and put the book on the pencil crayons, and you'll see that suddenly moving it is a lot easier. All right, that's rollers. Back I go.
Now it's time for Science So Simple, a Caveman Could Do It. This is a caveman. This is a rock.
Knock!
It is a well-known scientific fact that if this caveman were to try to move that rock, he would not know how to do it easily. Poor caveman. But in ancient times, people learned how to move heavy rocks using ropes
No!
and rollers.
Oh, wrong Earth.
Yes, rollers.
Wrong Earth.
Rollers.
Wrong Earth.
Close enough. Rollers make it much easier to move a heavy object. But they aren't perfect. So the wheel was invented. The wheel is a simple machine and one of mankind's greatest inventions. But no, that's not how it works.
No?
wheels go on axles, which go under a platform. Now you have something to place that heavy rock on to move it around. But all these great inventions came after the time of the caveman. Cavemen had to do everything the hard way. Join us next time for more science.
Okay, I've got rollers. They're just plastic pipes, but they'll work perfectly. I put them here. And now to lift up the machine. Okay. Perfect. And so the rollers go underneath like that. And then whoa. Whoa, careful. Look at that. No problem. Wait, I gotta get rid of this to get it moving. Now, the trick with rollers is you have to keep taking them out of the back and putting them in the front. But, whoa, whoa, whoa. It's stop, rollers, stop. Oh no, oh no. Okay, okay, whoa, rollers, easy. There we go. Okay, in the front, roll it forward.
Now I know what you're thinking. You're thinking this seems like a lot of work. And it's true, moving the rollers back and forth does take some time. But did you know this was how the pyramids were built? It's true. Giant stone blocks were moved on rollers just like I'm doing here. And as you can see, what worked for the ancient Egyptians works for me too. Uh-oh. Yeah, there's a hill here. If I go down the hill, it's gonna start rolling faster than I can do the rollers. I'm gonna need some help. Oh, I know! Pulleys! Pulleys! Pulleys!
Okay, pulleys. Pulleys are a great way to change the direction of force. I've got a rope going through this pulley and down to a book. So when I pull the rope down, the book goes up. Changing the direction of force can be very helpful, but pulleys can be helpful in another way. Pulleys can let you lift something that you couldn't normally lift. Now the rope goes up and down and up and down and up and down. And the force I need to lift this cinder block is a lot less than if I was just lifting it by myself. But I've got to pull a lot more rope. That's called mechanical advantage. Spreading out the force over a longer pull so you can lift a larger weight. If you use more pulleys, it reduces the amount of force. One pulley, same amount. Two pulleys, half the force. Three pulleys, 1/3. So I've got 5 pulleys here, which means I only need 1/5 the force to lift this cinder block. So there you go, pulleys. Now back to the, wait a minute. This calls for a mini-max. So how much weight can you lift with pulleys? Well, as much as you want, really. I have 4 pulleys on the bottom and 4 pulleys at the top. That means with 8 pulleys, I only have to lift 1/8 of my weight plus the weight of the chair I'm sitting in. And if I keep pulling, you will see that the chair I'm sitting in is roped to the pulleys. So now we see if I can pull myself up with nothing but pulleys. Look at that! I'm totally lifting myself into the air with the power of pulleys. And I don't need to use 2 hands. In fact, I only need to use 1 finger to hold myself up. And my thumb, obviously, to hold the rope. That is the power of pulleys. I could almost make myself fly. Well, almost. Now, back to the particle impulse controller. Letting myself down. Whoop. Whoop, whoop, whoop. Particle impulse controller. Let's go. Wait. All right, I've been able to use this pulley to lower it down the hill at the speed I want to go. Interestingly, I'm using the pulley not to make it lighter, but to just change the direction of force. And I managed to get it right here at the bottom. Now I've got to get it up onto the loading dock, so I think this is where I need a ramp. Whoa, whoa, oh. Here is something mind-bending you can do with pulleys. These buckets are attached to the table through a pulley. There's nothing holding this table up except for the weight of the buckets pushing down on the table. So if I took the buckets off the table, the weight of the buckets pulls the table up. But because the buckets are on the table, everything is in balance. Mind-bending, right? Okay, wait, it gets better. If I took a weight and I put it on the table, the weight of the buckets isn't enough to keep the table up. So I have to add more weight to the buckets so the buckets pull the table up. Whoa. And there you have it. It's weird, it's mind-bending, it's science. Okay. Ramps. Ramps are a great way to move something up. I will demonstrate using, you guessed it, a book. Let's say I wanted to move this heavy book on top of this stack of books using just this little string. Watch what happens. The string breaks, but if I built a ramp to get the book on top of this stack, and I use the same kind of string, watch what happens this time. Oh. You see, the ramp distributes the force, so you use less force to pull the book over the same amount of distance, and I can get it up to the top of the stack of books, and the string doesn't break. So ramps, let's put them into action. Woo. My simple machines have worked great. I've managed to get the particle impulse controller all the way to the loading dock. But now it's time for the hardest job. What I need to do is build a ramp that goes from the ground up to the loading dock. Then I need to pull the heavy impulse controller up the ramp. The best way to do that is to use a system of pulleys. I have 3 pulleys on one end and 2 pulleys on the controller. Because I have 5 pulleys working together, I'll only have to lift 1/5 of the weight. The plan is to get it tipped over onto the ramp, then use rollers to help it roll up as I pull on the rope. There's 3 pulleys on that piece of wood over there, and I got 2 pulleys on this piece of wood here. And now, if I pull, and I carefully put the rollers underneath, careful, careful. Perfect! Okay, now it's on the rollers, and now I can pull it up the ramp. Now I gotta carefully put new rollers underneath as I go. Pull it up the ramp. Roller.
I know what you're thinking. It still seems pretty difficult. If only the simple machines could give me longer arms. Well, they can't do that. But what they can do is give me the strength to do this heavy job with no one else around but me.
Hopefully that won't be a problem. There we go! I did it! All the way across the parking lot and up onto the loading dock with the help of levers, rollers, ramps, and pulleys. The hard part's done. Now I just have to get it into the lab. All right, let's see if all that effort was worth it. I think it's working! Well, there you go. Thanks very much for joining me on Science Max Experiments at Large. I think I'm gonna go home because it's been a long day and I could really use the rest. See you next time. Wait, I hit 3, 4, 1, 2. I should have hit 3, 4, 2, 1. Yeah, that's okay. I'll just go back and, Hey, welcome to Science Max Experiments at Large. I'm Phil McCordick, and hold on a second, I'm just gonna change. Okay, that's better. Now, where were we? Oh, right. Let's go make a boat. So you know that some things float and some things sink, like rocks, or wood, or full water bottles and empty water bottles, or carrots, foam, waffles, screwdriver, playing cards, plasticine, tinfoil, potato, my watch. Wait, that wasn't supposed to go in there. So how do you make a boat? You make it out of something that floats, right? Well, most boats are actually made out of metal. Tinfoil is metal and, well, it sinks. But if you fold tinfoil into a boat shape, it floats. And boats don't only float themselves, but they can hold people and cargo. In fact, there's container ships crossing the ocean at this very moment that are holding thousands of tons of cargo, and they're all made of metal, which doesn't float, it sinks. So how do boats do it? Are they magic? No, of course not. Boats are science. And here, you can be science maximites. Get some tinfoil and cut it into the same size pieces and fold a couple different shapes of boats and see which one can hold the most weight before sinking. And now it's time to max it out.
But before we do, here's how you can fold your own tinfoil boat in less than 15 seconds. First, take a square piece of tinfoil, then fold it in half. Fold one corner down and the other corner down. Then open it up and ta-da, you're done. If you want instructions on how to fold a more complicated boat, go to our website.
I have a feeling I'm gonna need a few extra lab coats for this experiment. Like I was saying, let's max out the tinfoil boat and find out a little bit more about why boats float. Okay, well, I'm here at an indoor pool, which is not, I wasn't expecting to be in the pool just yet, but this is where we're gonna build our giant tinfoil boat, so why not? Who's Nia?
Phil, you're wet.
I thought I was gonna come in over there, but I came in on the water sled. I think I had the coordinates wrong. Anyway, this is Husnia, and she's from Let's Talk Science, which is all about science education, right?
Yes.
Just like us. So you're gonna help me max out the tinfoil boat. I think I dropped it in the water. Hold on. Whoa! Here, where? Here it is. The tinfoil boat.
Phil, this is a boat?
Well, it looked a lot better before I came down the water slide, but that's the idea, and then we make it bigger. What do you think?
I don't think it's gonna work, Phil.
Oh, well, why not?
Tinfoil is very thin,
Uh-huh.
and it might not hold the shape of the boat.
Well, I still think we should use tinfoil, though.
Why?
Well, because the small experiment was tinfoil, and I bought all of this tinfoil.
Then let's do it.
Tinfoil?
Tinfoil?
Okay, high five. I will, I'll take the tinfoil, and you take that, and, I'm gonna have to dry off at some point.
Welcome to Shipbuilding for Pirates. I'm Swubby, and I've built some of the finest pirate ships for some of the finest pirates this side of the Caribbean. And I can teach you to do the same. But first, you need to know your basics. Mass and volume. Let's start with volume! But not that kind of volume. Which of these two chests do you think has more volume? Right, this one here. Which of these two balloons do you think has more volume? Right, this one here. Volume is how much space something takes up. Which of these two chests has more volume? That's right, they're the same. But which of these two chests has more mass? Which is heavier? Hard to tell, isn't it? But what if I told you that this one was empty and this one was full of treasure? Oh, loonies. Now, which one has more mass? That's right, this one. These two chests have the same volume, but this one has more mass. This chest has more volume than that one, but this one... My loonies! That chest does not have as much mass. Volume is how much space something takes up, and mass is how heavy something is. And when you look at them both together, you're looking at density. Join us next time on Shipbuilding for Pirates, and then we'll look at how volume, mass, and density work together to make something float. Oh, my precious, precious loonies. Are you all right, my pretties? They can't talk, so I'm not sure what they're saying.
So, Husni and I get to work constructing a large tinfoil boat. Our first design is just sort of a square, folded together out of a very large sheet of tinfoil. Simple, but can I ride in it? There we go. A giant tinfoil boat, just my size. Woo-hoo-hoo-hoo.
I don't know if it's gonna work. It's too thin.
You think it's too thin?
I feel like yes.
Well, what should we do?
Do you want to test it?
Let's test it. Okay, good idea. So here's the most important question. Do you want to test it or should I test it?
No, you test it.
All right, here we go. Putting it in. First test, does it float on its own? Yeah! Floats on its own, no problem. If I just get in very carefully, then it will work fine. See, if I'm careful about how I get in, no, it's fine. See, if I just get in like that.
Oh my... Phil, are you okay?
Wait a minute. It's sort of, no, that's just air. You know what went wrong? It wasn't boat-shaped. I think if we make it look more like a canoe, because canoes float, if we make it look like a canoe, it'll work great.
No, Phil. We need some support. If we add a couple of structures in between, then we add support to it.
I'll tell you what. Let's make a boat like I want to make and a boat like you want to make, and we'll see whose is the best.
That's a good idea. Okay, let's do that.
All right, let's do it.
Welcome back to Shipbuilding for Pirates. I'm Swubby, and now we know what volume means, what mass means, and that together it can tell you something's density. Now let's find out why things float. Let's say we're out to sea and my treasure chest gets swept overboard. Oh no! But it's all right. It floats because it pushes enough water out of the way, displaces it to carry its mass. But what if my treasure chest had more treasure in it? Well, we're giving it more mass, but not more volume. Too much mass and not enough volume, and it will sink. Oh no, my loonies! You need more volume if you want to float more mass. And that is why things float. I'm Swabby, and thanks for joining me on Shipbuilding for Pirates.
So, the first version of the tinfoil boat didn't work out too well.
Like that.
But my idea is to build a tinfoil boat more like a canoe to see if a different shape makes any difference.
Tinfoil canoe!
Very Canadian.
Very Canadian. The canoe part, anyway. I don't know about the tinfoil part. So, Husni and I had a bit of a disagreement of why the last boat didn't work. I thought it was because it wasn't shaped enough like a boat. So this one looks like a canoe.
What I thought is that it requires some structure.
Structure so that it wouldn't fold together.
That's right.
And we'll see how it goes.
All right.
All right, here we go. Did it work?
Nope.
Okay, your idea next. Did you know it's easier to float in salt water, like in the ocean, than it is in fresh water, like a lake or a pool? That's because not all liquids are created equal. They have different densities. This is fresh water, or it doesn't have anything in it. And this is sugar. If I was to put 1 scoop of sugar in this water and stir it around until it dissolves, now this liquid is more dense than before I put the sugar in. Here's an experiment you can do at home using liquid density. This glass just has regular water with yellow food coloring in it. This glass, green food coloring and ½ a cup of sugar in it. This one has a full cup of sugar in it, and this one has 2 cups of sugar in it. Now, when you do this at home, you'll definitely want an adult to help you because you have to heat the water if you want to dissolve that much sugar in 1 glass of water. I'm gonna put them all in 1 container. You can do this at home, and when you do, I suggest you use a very small container because you have to be very careful when you put the layers in. You can use a turkey baster or a straw. When you put your finger on top, the air pressure will hold the liquid in and you can just drop it in. But these kind of take some time, so I'm going to use the syringe of science. I'm gonna use the most dense liquid first because that's the one that's gonna want to be on the bottom. I carefully put it on the bottom of the container. The next layer, be very careful. And you'll see that the red and the blue aren't mixing because they have different densities. The blue is heavier than the red. We'll add the green, and you can see even when it drips into the red, it comes back up to the top because the green liquid isn't as dense as the red liquid, and the denser liquids push the lighter liquid up. And now we're gonna add the yellow, which of course has no sugar in it at all. And there you go. All the layers stay separate. If you put it on a light, you can really see it. Liquid densities. Now, let's max it out. Ta-da! The longest length of liquid layers. 12 liquids all organized by density. Starting from the bottom, we have honey, corn syrup, chocolate syrup, maple syrup, dish soap, whole milk, water, dyed blue, vegetable oil, extra virgin olive oil, rubbing alcohol, baby oil, and lamp oil. Liquid density. I really, really want to mix it up, but it took me a long time to make this, so I'm not going to.
Our first 2 attempts at a tinfoil boat haven't gone so well. Husnia's idea is to make a tinfoil boat and add some more structure, because the tinfoil just wants to collapse when I get in it. So we start with a large piece of cardboard on the bottom, then we wrap the tinfoil around it and shape it into a boat. After that, we add some supports across the top to stop it from folding in when we add my weight to it.
This boat feels a lot stronger than the one I was just in.
I told you.
So how does all of this work?
So we got some support using broomsticks and then some cardboard paper. And then underneath we have cardboard.
And so how will all of this help the boat not sink with me in it?
Right. The broomsticks will prevent it from folding this way and you won't sink.
Good.
The cardboard will prevent it from folding this way and you won't sink again.
Not sinking is my favorite thing to do in the tinfoil boat. All right, so let's try it.
Let's do
now,
it.
Are you gonna get in this one?
I'll tell you what, Phil. If you get in and you don't sink, I'll go after you.
Deal.
All right.
All right, here we go. It's sort of working. Oh no, water's coming in. It's sort of working.
It's almost working.
Uh-oh.
Wow.
No.
Hold on.
1, 2, 3, go.
Another thing I learned is that a very light tinfoil boat can be very heavy when it's full of water.
I don't know if fixing it is in the cards. I think we're gonna have to build another boat.
So what do you think we should do?
Let's add more structure.
More structure.
Oh, yeah.
What if we add like a metal rod around the outside and maybe some more metal rods and ribs? And we wrap it all in tinfoil, and you think it'll work?
Let's give it a try.
Let's give it a try.
Don't worry about it. I got this.
No, I get it. I'll get it.
Sure.
Who wants to do an experiment with diapers? Oh! No, I'm serious. You may have a little brother or sister at home, which means you probably know where you can find some diapers. But there are 2 things you need to remember. First, ask an adult if you can use the diapers for your experiment. And 2, only use unused diapers, okay? Okay. So, you take the diaper, and if you cut it, be very careful, maybe get an adult to help you, over some black construction paper, like I have here, and you shake the diaper over the construction paper, you'll see that there's a little powder that comes out. And this is the secret ingredient. This is super absorbent gel. And what it does is it soaks up all the liquid, and diapers are full of them. And you carefully pour it into a plastic cup, like that. Now you can see I have already done it with a number of diapers. It's important to use a plastic cup because it's a little messy, although it's non-toxic, it's totally safe, but it's still easier to clean up by just throwing the cup away. Now, add some water, and what happens is this super absorbent gel absorbs the water and turns very quickly into a paste. Look at that. Now, let's max it out. 5 kilograms of super absorbent gel, 500 liters of water. Now, it is time to do science! And I have my own stir stick. Yep, definitely coming along. I'm not exactly sure if we're getting anything on this camera, but I want to make sure it's recording. Yep, it's recording. There we go. It is definitely turning solid. Well, there you go. The giant super absorbent gel experiment. Corey, Trevor, I need some help getting out. How many outfits have I been through in this episode? How many outfits have I been through in this episode? Anybody have a towel? There you go. Thanks, buddy. That's great.
Husnia's idea of adding structure to the tinfoil boat was definitely right. We just needed to go further. So we did it again. This time, we made a much larger boat. We started with a sheet of cardboard, then wrapped the tinfoil around and added some metal supports taped to the cardboard across the boat this way to make ribs, as well as some other supporting pieces in the front and the back. Then another metal rod all the way around the top, and finally, supports across the middle.
All right, feel how strong it is. I'm really excited about this version of the tinfoil boat. What we did is we used thwarts, big hard pieces of wood that we did last time, but this time we have ribs.
Ribs, right, which are made of a cardboard, a metal rod attached to it,
And shaped, and we did a whole bunch of them in the whole length of the boat. And then we used all of this bendable metal, and we have one that runs all the way around the gunnels, and a whole bunch that run down the inside, and we even used bike fenders at the front and the back of the boat to give it super rigidity so that it hopefully won't go like all the other boats have done so far. Are you ready, Husnia?
Let's do this.
1, 2, 3, lift. All right, let me get over. It floats, but that doesn't tell us anything because they've all floated at this point. It's only when I get into it. Okay, here we go. All right. Hey! Hey, it works! All right.
Oh, it's working.
Ha 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 ha! Look at that! It works perfectly. The tinfoil boat experiment has been done. Science Max, experiments at large. What do you think, Husnia?
The only reason I got into this boat because I knew it's gonna work.
Really?
Oh yeah.
So you knew you would never get wet? See, I don't think that's fair. I think it's time that you got wet. I think we should go. I think you and I should just get wet right now. Just need
Someone help.
You're still dry, aren't you? That is so unfair. Behold the power of states of matter! Greetings, Science Maximites! I'm Phil McCordick. I think I overdid it with the fog machine. This is Science Max, experiments at large. Can you even see me? Let's go over here. Today we're talking about states of matter. Now there are 3 main states of matter. Solid, like this table, liquid, like the water in this beaker, and gas. Yes, thank you. And we're also gonna be looking at the things that kind of go in between. Things that are sometimes solid, sometimes liquid, like cornstarch mud, which is very easy to make. All you need is water and cornstarch, which you can get at the grocery store. Mix it up however much you want. Just remember, 2 parts cornstarch to 1 part water. Twice as much of this than you have of that. Very easy. Mix it up and you get cornstarch mud, which sort of seems like a liquid unless you hit it. And then it becomes solid. But if I pour it, it's a liquid. Even if I hold it in my hand and I hit it really fast, it turns into a ball, and it will stay in a ball as long as I keep hitting it or squeezing it. But soon as I stop, it turns into a liquid again. Now, we're gonna max this out. We'll go through the portal and learn more about solids, liquids, and gases. Yeah, right. That's why I'm going to the Center for Skills Development and Training. Oh, no, wait, that's the code for the fog machine. Wait, stop. Stop, it seems to be stuck. Oh, never mind. I'll fix it later. Right. Hey, Judy, how are you?
Hi, Phil. How are you?
Good. Judy is going for her PhD in chemistry, right?
Yes.
Fantastic, because that means you can explain cornstarch mud to me. Now, is this a solid or is it a liquid?
Well, it kind of has properties of both. It's called a non-Newtonian fluid, so that makes it a liquid.
A liquid? Well, I mean, it pours like a liquid, but when you hit it, it's a solid. So why does it turn solid when you hit it?
So when you're pouring it, the particles are still far apart, so they can't interact with each other, and so they stay a liquid. But when you're hitting it, you're jamming the particles together, and they line up to become a solid.
Now, does it still work the same way if we have a lot more of it?
It should.
Great, because I've got this 20-kilogram bag of cornstarch, and I have 34 more of them.
Wow, that's a lot. But I think you'll need a much bigger container.
Much bigger container, great. I got some wood over there. Why don't you go, and I'll follow you.
All right.
I'll follow you. I'm coming. Yeah, thanks, Ramona. And give me one of them fizzy drinks. Not too fizzy, just sort of medium fizzy. Thanks a lot. Hello, do you have trouble knowing what is a solid, liquid, or gas? Are you confused by Jell-O? I mean, which is it? Is it a solid or is it a liquid? Water is a liquid, but what about when it's ice? Well, you gotta know your states of matter. There are three main states of matter: solid, liquid, and gas. And there are three rules that you need to figure out which one of them is which. Does it flow? Does it fit the shape of its container? And can you squeeze it? Rule number 1, does it flow? Solid, liquid, gas. Here's a gas. Does it flow? Do the particles pour over each other and cascade down? Yeah, they do. Does a liquid flow? Yeah, it does. Does a solid? Nope. Rule number 2, what happens when you put it in a container? Does it take the shape of the container? Gases take the shape of the container. Liquids takes the shape of the container. Solids do not take the shape of their container. I know what you're thinking. You're thinking, I get the whole pouring and taking the shape of the container, but come on. Liquids and gases, they do both of those things. Well, it all comes down to rule number 3. Can you squeeze it? Now, solids, you can't really squeeze them. Liquids, you can't really squeeze them. Gases, bam, you can squeeze them. You see, gases compress. Liquids and solids, they don't really compress very well. The other difference between gases and liquids is gases will take the shape and the volume of the container they're put in. Liquids don't do that. So there you go. Solid, liquid, gas. And the rules. Does it flow? Does it take the shape of the container? And can you squeeze it? Now you know your states of matter. That'll be $6.50. Cash only.
So what is cornstarch mud and how does it work? Well, cornstarch mud is a non-Newtonian fluid, which means it behaves differently than you, or Newton, would expect. Here's cornstarch, and here's water. Cornstarch is made up of large, blocky molecules like this. Water is made up of much smaller, rounder molecules like this. When you put them together, it looks something like this. It all has to do with how the molecules slide past each other. When you put light pressure or slow pressure on the mud, the water molecules and cornstarch molecules have time to shift out of the way. But when you put a sudden pressure on it, the water molecules squirt out of the way, but the cornstarch molecules don't have enough time. So you get a section that's nearly all cornstarch, which acts as a solid. Cornstarch mud is a shear thickening fluid. Shear is talking about the force of things sliding around, in this case, the molecules. So when the shear force is strong, the fluid thickens. Shear thickening. So here's the plan. If Judy and I make enough cornstarch mud, could we run across it? Let's find out.
Yeah, I think mine is just the right consistency. How's yours, Judy?
I think I'm ready too. This is much harder than I thought.
Yeah, it's really hard to get it mixed at the very beginning, but mine is ready to go. Okay, here we go.
Sounds
First
good.
batch. You ready?
Yep.
Dump it in. Woo! Woo! I thought that would be more.
I thought so too.
It's really not filling this up very much, is it?
No.
Huh, that's a lot of cornstarch. This is great, but I think we're gonna have to go a little faster than this.
I think we need some sort of mixing device.
Yeah, I mean, we don't have to do this by hand. We can get some sort of machine to help us.
Yeah.
Right on, high five.
Oh.
We shouldn't high five when we have this stuff on our hands.
Nope.
Yeah, good call. This science is delicious. This is rock candy. It's basically crystallized sugar, and you make it by turning a solid into a liquid and then back to a solid again. Here's how you can make it at home. You need a container that you're not gonna need for a while, and some water, some sugar. You can use brown or white. I like to use brown. And an adult. Here's why you need an adult. You want to dissolve 3 cups of sugar into every cup of water, and you can't do that unless you heat the water. So get an adult, a saucepan, and heat the water up, pour the sugar in, and keep stirring until it's all dissolved. Then pour it in your container and let it cool down. Then you'll need a shish kebab skewer, which is something you can get at the grocery store. Cut it down to the right size so it fits nicely into your container. And then dunk it in your sugar and get some crystals coated around the stick. These are seed crystals, and they get the whole process started. And now you have to wait for these to dry, otherwise they'll just fall off the stick when you put it in the water. So I've got one here that has dried out. You'll also want something to keep it from falling in the top of the container, so I'm gonna use a clothespin. Put it in there and dunk it in the container like that. And now for the final step, if you want, you can add food coloring. I like to use red because it reminds me of science. And I'm gonna use the stick to actually stir that up a little bit. There we go. Now, the dissolved sugar crystals in the water will slowly grow on the crystals that are already attached to the stick, and it will eventually grow into a rock candy pop. But it takes about a week. No, I'm just kidding. I've already got one that's standing by. Here we go. This one has been growing for about 7 days. And there you go, rock candy. Delicious science. Now, how can we make this any better? I mean, it's crystallized sugar. It doesn't get any more maxed out than that, does it? Yeah, it does. Come on. This is a giant container of sugar water, and I've been brewing a massive rock candy crystal in it for a while, but it's sort of getting a little bit too big to fit out the top of the container, so you know what? I'm just gonna put that back in there and chalk that one up to science because, well, eating a rock candy crystal that big would definitely not be good for my teeth, so yeah.
So our big experiment is to take a whole lot of cornstarch and fill a trough to see if we can run on it. But mixing it by hand was going to take forever. So Judy and I got a drill with a mixing attachment on the end.
Whoa, sorry. All right, so Judy, I'm noticing a bit of a problem here.
What is it?
Well, if I mix at the top, everything's fine, but as soon as I get it a little bit deeper, and then it gets really tough, and the whole bucket starts to spin, and the drill stops.
Yeah, I think it's because the drill's trying to mix it too fast. When we're mixing it by hand, it's slow and you can still let it stay a liquid, but now you're just making it a solid.
Right, because it's a sheer thickening fluid,
Exactly.
so if you hit it really quickly with something, like the blades of this spinning really quickly in the thing, it'll suddenly turn into a solid, and it'll be really hard to mix.
Yep.
So we go slow. Going slow. Going slow. Suddenly realizing that if we go slow, we'll be here forever.
Yep.
You know what I think we need? Whoa, sorry. You know what I think we need? We need a different way to mix this.
Yep.
We need a way to mix more of it, and we need a way that it doesn't hit it with blades that suddenly go through it really quickly.
Something that can mix on a large scale, but slowly.
I have just the thing. Come with me.
All right.
The interesting thing about bubbles is they're a gas surrounded by a liquid. So get some dish soap and some water, and then be Science Maximites and find things around the house that you can make bubbles out of. Just about anything that has holes will do.
Or I like this one. I call it the loud bubble. Or
Now it's time to max it out. I'm here at the Ontario Science Centre, and this is Anthony. Hey, Anthony.
Hey, how's it going?
Good. So you are amazing at bubbles.
I am. I've been practicing for a while. Let's get started.
Okay.
You're gonna make an okie dokie sign like this.
Uh-huh.
You're gonna dip it right into our bubble solution. Come on, get right in
Okay,
there,
right
right in
in.
there. Make sure you get it all. Oh, that's a little too much.
Well,
That's
then I
good.
can make two.
And then you're gonna keep that okie dokie sign. You're gonna blow very gently.
Nice.
I brought these two giant sticks here, and I don't know if you noticed, but I've got a smoke machine here.
Right.
So we'll turn that on, and then if you press that green button there, you're gonna shoot some smoke, and we're gonna try to catch that smoke in a giant bubble. You ready? Okay, and I'm gonna try to... Oh, that was so close. Did you see that one? You give it a shot. Nice! Oh, check that out! That was amazing! That was huge. Try it again. Let's see if I can get the smoke machine. Here we go. Go for it, go for it. Push right towards. Oh, check that out! You did it! Look at that! Look at that! No! Smoke, and it bounces on the floor because the floor, it doesn't have any oils like our hands do. Isn't that amazing?
That was
oh my
great.
God, that was so cool.
That was great.
You know what I think we should do?
What's that?
Giant bubble, tons of smoke.
Done.
Okay, here we go.
Let's do it. You ready?
Giant bubble, tons of smoke. Go.
Awesome! Oh my God! Look at that! Amazing! Look at that! That's crazy!
Maxed out bubble. Well, there you go. Giant smoke-filled bubbles.
Awesome!
Yeah.
Judy and I tried mixing the cornstarch mud using a drill with a mixer attachment, but it didn't work. We should have known better. Here's the mixer in our cornstarch mud. Usually, a mixer works by going really fast and mixing everything together. But remember that cornstarch mud is a shear thickening fluid. So, when the blades of the mixer tried to go fast through the cornstarch mud, it did what it always does, turn solid. The faster and harder you try to move it, the more solid it will become. This means the only way to mix it would be if we made the drill go very, very slow, which wouldn't speed things up at all. So with the drill another lost cause, Judy and I need the biggest thing around that could mix stuff up.
Come on back. Good. Little bit more. Perfect. A cement truck is a perfect thing to mix because all we have to do is get all the cornstarch up in here and it'll mix it, and it doesn't move it too fast. It goes nice and slow, so hopefully a shear thickening fluid will be fine. I'm gonna get Judy. She's driving the truck. Hey, Judy, that's perfect.
The only problem is we needed to get all of those bags of cornstarch into the hopper of the cement truck.
I didn't think it'd be this messy.
We needed to call the entire Science Max build team to help us out.
This is possibly the messiest thing I've ever done. Awesome! Woo. Hey, Judy, you wanna lift up any bags?
I'm okay, thanks.
That's okay. I'm having a lot of fun, so I can do them.
Cool.
Oh no! Oh no! Oh no! Yeah! I got most of it. All right, I think we're done. I think that's enough bags. Let's start the mixing! So, what do you think, Judy? Do you think it's gonna work?
I think so, because you're mixing at a very large volume, but at a very low speed.
Yep.
So throughout the process, it'll stay a liquid until we're ready to run across it.
That sounds exactly like the kind of science I like to see. You know what I really like is that every time I move, more cornstarch comes off. It's like I'm a human fog machine. This is liquid nitrogen. Nitrogen makes up most of the air we breathe, but if you get it really, really cold, it turns into a liquid. The fun thing is you can use it to make other things really, really cold too, like this banana. I have frozen this banana solid thanks to the liquid nitrogen, and normally a mushy banana would not be able to hammer in a nail, but whoa, because it's frozen, I can hammer this nail into this block of wood. So that got me wondering, if I can turn a banana into a hammer using liquid nitrogen, could I turn a pumpkin into a sledgehammer? Let's find out. Pumpkin sledgehammer, take one. No, I think the answer is no. You cannot turn a pumpkin into a sledgehammer with liquid nitrogen. All you can do is make a really, really big mess. I'm gonna have to clean this up, aren't I?
Now we have a cement truck to help us do the mixing for our cornstarch mud. After making a giant mess getting the cornstarch into the cement truck, it's time to see if it worked.
Hey, Phil, how's it going?
Yeah, it looks like it's mixing pretty well. I'm really glad we're not doing this by hand, because it did take a really long time. We've almost got it at the right consistency, but it's taken some time. But it's getting a little dark out, Judy. I don't know, do you want to quit and go home?
No.
Of course not. That's not what we do in science. Oh, here we go. Yeah!
Awesome.
All right, let's see it. Let's see if it's... I like how it comes down in little steps. And look, it's working just like it should. I hit it, and it's solid, but you can see it's pouring like a liquid. Yeah, here comes a big wave.
Wow.
Here it comes. Oh! Wow!
And it's totally filling up.
Oh yeah, filling up really fast. I think we should stop pouring very soon.
Yep, we may not have a big enough trough. Yep.
Liking it.
It's good.
Yeah. I think it's time. It's not even done pouring, but I'm gonna try it. Okay, you ready? Whoa.
Oh, and you did it!
Whoa. You have to get back onto the sides before you stop moving.
Or else it becomes a liquid.
All right, it's your turn.
Okay.
Here.
Go.
Okay, ready?
Okay.
You gotta hit your feet really fast.
All right.
Here, go. Yeah!
This actually works.
Because cornstarch mud is a sheer thickening fluid, it means it stays a liquid until you hit it suddenly, like with your hands, or in this case, our feet. And then it turns to a solid. So as long as Judy and I keep slapping our feet down with enough force, we can walk on top of it.
One more dance.
All right.
And
let's
tell you
do
what,
it.
we'll do one more dance.
All right, let's do that.
Okay, ready?
All right.
And go. All right.
All right.
Yeah, there you go.
We've done it.
Solids, liquid gases. Thanks very much for joining us on Science Max Experiments at Large. Woo!
Greetings, Science Maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the balloon-powered car. Here's how it works. Woohoo! It all has to do with Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
We don't have to do this now. This is all for later. We can build the cars first, and then we can, let's go over here. So how do you build a balloon-powered car? Well, I suggest you be Science Maximites, because there's any number of ways you can build a balloon-powered car. You do not have to follow my design. You should come up with one of your own. It may even be better than the one I built. But I will give you some tips, though, that make it a lot easier. First of all, you need something to stick your balloon on that has an opening on it. I used a turkey baster for this car. I just pop the top off, and remember to tell an adult that you're using the turkey baster, and then you stick the balloon on there, and it allows you to attach something to the car, and it also makes it easier to blow up the balloon. You can use any number of things, even just any kind of tube that you find lying around. It helps you attach the balloon to the car, and it helps you blow up the balloon way easier. The other thing you should think about when you make your balloon-powered car is how you're going to make the wheels roll. Once you've decided on the base of the car, you could use anything, even just a piece of cardboard like this. You can do your wheels in two ways. The first way is to attach the wheels to the axle. This is how I made the axle of this car. I used a shish kebab skewer, and I stuck it inside a straw, just like that. And then I attached the lids to the shish kebab skewer. So the lids and the shish kebab skewer are attached, and they rotate in the straw. That's one way to make the wheels turn. The other way is to tape down the axle or whatever you're going to use and have the wheels spin around on the axle. Two great ways to make your wheels turn, and it really kind of depends on the wheels you're using. You can make your own design and keep refining it and making it better and faster, or do what I like to do and make a whole bunch of different cars. So we've got this one. This one I made out of paper plates, and this is a snorkel.
Awesome. This one is the rock car, because there's a rock on it. I've got the dragster model. It's a long broom handle, and it might not work that well, but who knows? And this is my favorite design. It's made out of waffles and an ice cube tray. This is why I make a whole bunch of different cars, because I can race them.
Sunday, Sunday, Sunday at the Science Maxidrome. It's the balloon-powered car winner-take-all drag race of awesome.
First up, the Eliminator.
Woohoo! Better late than never, it's the Procrastinator. Crushing the competition, it's the Terminator! Feel the chill of the refrigerator. And last but not least, the, Regurgitator!
Well, when you build your balloon-powered cars, you can figure out what worked or what didn't work and try modifying your designs to make them work even better. That is science. And now we're gonna max it out, because this is Science Max Experiments at Large. So we're gonna take that small balloon-powered car that we just built and we're gonna make it much, much bigger. I'm gonna go to the Center for Skills Development and Training, and we're gonna use the science behind the small balloon-powered car, and we're gonna make it big. That science is Newton's third law, but there's plenty of
third law. For every action,
there's plenty of time for this later. We're not doing this bit now. We're doing that bit in a minute. So we can, no, I said we're doing it later. We're doing it later. Here. Whoa. Hi, Sarah.
Hi, Phil.
This is Sarah, and she's got a master's degree in physics from McMaster University.
That's right.
And we're gonna be talking about Newton's third law. Oh, look out, duck. Sorry. There was a sign that kept coming in. Never mind. Newton's third law. Well, what is that?
For every action, there's an equal and opposite reaction.
Right. So how does that work with our balloon car?
Ah, cool. Okay, so if you blow up the balloon, what's gonna happen when you release it is the air is gonna push out with a certain force, which in turn is gonna cause the cart to move forward with the exact same force.
Yeah, works great. So how come it doesn't work with my rock cart?
Ah, wow. Well, actually, it did work. So the balloon still pushes with the exact same force, which causes the cart to have the exact same force push forward, but your rock is really heavy, so you probably didn't see it move.
Oh, so a lighter cart works better with the same amount of force.
That's it.
Well, there you go. Newton's third law. What?
Newton's third law. For every action, there is an equal and opposite reaction.
I'm really starting to dislike that sign.
Phil, are you okay?
Yeah, I'm fine.
Our small balloon-powered car works because of Newton's third law. For every action, there's an equal and opposite reaction. The air pushing out the balloon this way pushes the car with the same amount of force this way. So, in order to max it out, the plan is just to get a bigger wheeled cart and a much bigger balloon. So, everything should work out the same.
Okay, so sorry. Oh, I thought what we would do is in order to max out the balloon-powered car, what we need is a cart to start with, and then I ride it. And we have a giant balloon, and then I go.
Do you have a giant balloon?
Ha 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 ha! Giant balloon! So, step one, Sarah blows up the balloon.
Okay.
Wait. Use this air compressor, it'll probably be a lot faster.
Sarah and I get to work blowing up the balloon. And it takes a long time. A very long time.
Okay, human-sized balloon-powered car test. Take one. All right, Sarah.
You got it?
Yeah. Okay, let it go.
Okay, go.
Let it go.
I did.
You did let it go.
I just let go.
Nothing is happening.
It's not coming out fast enough, and you're a bit too massive. I don't think it's gonna work like this.
Really?
Yeah.
Okay. Balloon-powered car test 2. No fill. I'll just take it. What happened?
I don't think it worked. The balloon popped. Phil, are you okay?
This is why you wear protective eyewear. Yeah. So, that didn't work.
No.
No. Should we get another balloon?
I think we need something else.
Okay, well, the air coming out of the balloon just didn't have enough force, so.
We need the air to come out with more force.
Yeah, do we get, what, a bigger balloon?
I don't think that's gonna work. I don't think it's that. I think we need something with compressed air.
Oh, like a scuba tank or a...
Fire extinguisher, something like that. Yeah, that's what we need.
Okay, sure. Well, we can... All right, so I don't know if that's safe to do that, so we'd have to build like a cage or something?
Yeah, I don't know if it's gonna work on this.
All right, well, back to the drawing board. So
Okay.
what we should do is we should get
We need to find these tanks.
Get the tanks, and then we make like a frame out of aluminum or something.
Okay, that could work.
Yeah,
That's
they
a
can
good
hold the
idea.
tanks, so
Yeah.
they're safe. And then what we should do is...
Who was Isaac Newton? He was a mathematician and probably #1 on the list of top scientists of all time. Albert Einstein said, Isaac Newton was the smartest person that ever lived. You've got to be special if Einstein is calling you smart. Newton's 3 laws of motion was a huge idea, but did you know Newton also came up with the idea of gravity? The famous story is that in 1666, Isaac Newton was sitting under an apple tree when he watched an apple fall and wondered why. Hey everyone, I just invented gravity, which was a big relief because up until then, everyone was just floating around. Okay, so it didn't happen like that. He didn't invent gravity. He gave a name to this invisible force and then described how it works. Not only did it make things fall down, but it was the same force that kept the moon circling the Earth and the Earth circling the sun. And he invented a new kind of math to explain how. We now call it calculus. See? I told you he was smart. He's very smart. This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be Science Maximites and get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? Weird. Just don't eat it. Now, it's time to max it out. I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet, and half of me is dry. What's more, half of my outfit ended up being wet and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool, and I realized I should have duct taped the pocket, because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out, now it's keeping the water in.
Let's take a closer look at Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
Okay. All right, let's watch it back.
When the sign hits me, I exert a force on the sign in the opposite direction. That makes the sign stop moving. It also exerts an equal force on me, causing me to fly off in this direction.
Now, if I was to push this sign, I'm not only pushing the sign this way, but my feet are pushing against the ground in the opposite direction. It's, well, it's really easier to see if I'm not standing on the ground. Oh, hold on. Okay, so, okay. So now that I'm hanging, watch. I push on the sign, but when I exert force on the sign to make it go this way, I go that way. Well, actually, it doesn't work as well because the sign isn't as heavy as I am. So wait, I have this over here. This is a barrel, and it has stuff in it, and it weighs as much as I do. Okay, so watch. If I push on the barrel like that, I go away from it as much as it goes away from me. So, there you have it. Newton's
third...
No, hold on. Newton's
third law.
Newton's third law. Okay, go.
Newton's third law. For every action, there is an equal and opposite reaction.
So, using a giant balloon to push me on a cart didn't work.
What happened?
The plan now is to use the compressed gas cylinder. Just like a balloon, these cylinders contain a lot of air. If we get a cart and put a gas cylinder in a cage for safety on the back and open the valve, the escaping air might have enough force to push me.
This is 2 cubic meters of air. If we were to put it in a balloon, the balloon would be this big. But if we compress the air, we can fit it all into one of these, a steel tank. This is what we're going to be using next for our air-powered car. Got it?
Yep.
All right. So Sarah and I have been hard at work, and we've built the air-powered cart. We can't call it a balloon-powered cart anymore because now we've got a compressed air tank, so it's not a balloon that powers it.
Exactly.
Okay, so I'm gonna sit on here, Sarah's gonna turn on the tank, and I'm gonna go. And before we do this, we should say, do not, under any circumstances, try this at home. We are trained professionals. You ready?
I'm ready.
Okay, high five first. Okay, now we do it.
Okay, so before I turn the tank on, make sure your feet are down and the brakes are on.
Gotcha.
Don't take them off till I say go.
You have got it.
All right.
Ready?
Okay.
Yeah!
It worked!
Yeah, it did work, but I feel like it could work better.
You want to go faster?
I do want to go faster. This reminds me of the rock car.
Yeah.
Where we didn't have a big enough balloon.
We need more force.
We need more force. So should we get a bigger tank?
Let's get more tanks.
More?
Tanks, more force. You're gonna go faster forward. Newton's third law.
Newton's third law, high five. All right, let's do it.
All right.
Whoa. This is Newton's cradle, and it's a really cool toy that demonstrates all kinds of laws of motion, including Newton's third law. What you do is you pull this one ball out, and when it hits these balls, they exert force on that ball to make it stop moving, but it exerts force on these balls, which travels through the balls and makes this one on the end fly out, like that. Now, there's a lot going on here, but you can really see how the force is equal that you put in and you get out if you use 2 balls. I swing 2 balls up, and 2 balls go out that side. Isn't that cool? Now, it wouldn't be Science Max unless we maxed it out, so come on. Whoa! Okay, this is one we built out of bowling balls. Bowling balls. Bowling balls. Instead of smaller balls. And I think it's gonna work the same way. Let's find out. You throw one out and yeah, it works the same. Okay, now let's try it with two balls. Okay, ready? Wait. And two balls, throw them out. And two balls on that side. All right, so there you have it. Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
So our single pressurized tank created enough force to move me, but not very fast. The plan now is to do two things. First, we're going to triple the amount of thrust by using 3 tanks. We're also going to use some pipes that lock into each other to give me an initial push. These pipes slide together, and when the air is turned on, the pressure in the pipes will cause them to slide apart, which will push me forward. After that, I use what's left in the tanks to keep going.
All right, now it's time to max it out. I've enlisted the help of a few more Science Max people. Thank you very much, Corey. You'll see now we have 3 tanks of compressed gas, and we've also got this nifty little contraption. How does this work, Sarah?
All right, so each tank is attached to a tube, and you can see that each tube goes into this one main tube, so when we turn them on, pressure's gonna build up, and we're gonna go forward with more force.
Well, that's great, and Reed is stacking cinder blocks, thanks Reed, up so that will push, the pipe will push against the cinder blocks, and then I'll go that way. All right, well, are you guys ready?
I'm ready.
All right, let's do it. Now, again, I have to say, thank you, Corey, I've got it. This is something you definitely don't want to try at home. We are all trained professionals. We have a physics degree here. We've got TV people that make sure that this is safe. So watch it and enjoy, but please don't try any of this at home. Okay, I'm ready. Sarah, count me down.
3, 2, 1.
That was awesome!
That was really awesome.
All right, high fives, high fives. Yeah. And it's raining now, so it looks like we're gonna have to stop. So thank you very much for joining us on Science Max Experiments at Large in our episode on Newton's third law. Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're gonna be looking at the power of magnets. You see, magnets are fun things to experiment with because they are really, they're really interesting. This magnet that I've got here is a neodymium magnet or a rare earth magnet. It's one of the strongest magnets you can get. A magnet is an object that is attracted to anything that is ferromagnetic, which is iron, nickel, or cobalt. And magnets are interesting because they have 2 sides. There are two poles. I'd show you, but I can't get the chain off. Hold on one second. Haha. There are 2. Oh no. There are 2 poles to every magnet, just like the Earth. There is a North Pole and a South Pole. That's right, the Earth is a giant magnet. So, if you take kitchen magnets, you'll find that there's 2 different poles. I've written north and south on these ones. They don't normally come like that. If you put the north and the south together, they stick. But if you put the north and north or south and south together, they repel. They repel, see? They don't want to go together at all. And you can force them together if you want, but if you do, they will spring away the second you let them go. But when magnets repel each other, I find that some of the most interesting stuff. Check this out. This is just a small container, and I've got a magnet in here, and I have a loonie attached to it so that it fits nicely in the container like that. For the top, I've attached 2 magnets together, and I have another coin on it. And if you put them in there, I've made sure that the 2 poles repel each other, which means this magnet will just sit there and float. Magnetic levitation. Very interesting. And you can pop the top on that if you want and just carry around a levitating magnet. Now, there's a couple fancier ways you can levitate stuff with magnets. This is just a wooden frame I've made. This is completely not necessary. You can use just about anything in your house. A desk lamp works really well. The important part is I've tied a magnet to the end of this arm here, and this is a bolt, which is attracted to the magnet, but it's got a thread tied to it, so it can't get there. Just far enough that it will actually hang in mid-air. Look at that, it's not attached to anything, it's just being pulled up by the attraction from the magnet. The thing is, as soon as you pull the bolt away far enough, it will lose the attraction and it'll just fall. Very cool. Here's one that's a little bit more complicated, but is also really neat. This one uses disc magnets, which have a circle or a hole in the middle of them here, and you put 2 around a pencil and then 4 more in such a position that you can put the pencil against this wood on the side and it will just levitate on its own. You can even give it a spin. Look at that.
And if you want to make the levitating pencil yourself, there's step-by-step instructions on how to build an easy-peasy version on our website.
Meantime, we are gonna max this out. Magnetic levitation on Science Max Experiments at Large. But you're probably thinking, what are we going to levitate? Well, we're going to levitate meat. At least, that's the plan. That's why I'm going to the Center for Skills Development and Training. Come on.
Okay, who turned out the lights? Ow, what was that? Why is this room so small? And only going down to waist level. This is the weirdest room I've ever been in. Where am I? What's going on?
Hey, Matt.
Hi, Phil.
This is Matt. He's from Job Master Magnets. Now, you guys use lots of big magnets, right?
That's right, we do.
Awesome. So maybe you could help me max out this.
Wow. You did a great job of building the levitating pencil experiment.
Yeah, so what's going on here exactly?
Well, all magnets have at least a north and a south pole.
Right.
And when you put like poles together, they want to repel.
Oh, okay. So have you ever levitated a person?
Not yet.
Well, let's do it.
All right.
Do you think we can use these?
We can try.
Okay, well, put that one on the ground. And, okay, so north, and I'll put the north one on my foot here. And then if I just step, oh, wait a minute. If I step, stop moving. If I step on that, step on the, okay, well, first of all, this magnet keeps sort of moving away from me when I try to push down on it. What do we do? How do we fix this?
Well, we need to keep the magnets in position so that they don't move around when you try to bring them together.
Yeah, because I have to come straight down on it, don't I?
That's right.
So why don't we attach this one to the floor?
Good idea.
And then we'll put a board on this one, and we'll see how it goes.
Perfect.
Okay, let's do it.
All right.
This is a magnet. This is a magnet. This is a magnet. This is a shoe. What's the difference? To know that, you have to know your magnets. This is a donut. It does not stick to this magnet. This is a spoon. It sticks to this magnet. These paper clips stick to this magnet. This shoe does not. So what is attracted to magnets? Only things that are ferromagnetic. Here's the difference. Horseshoe, horseshoe magnet. This one is a magnet. This one is not. But the horseshoe sticks to the horseshoe magnet because this one's a magnet and this one is ferromagnetic. Only things that are ferromagnetic are attracted to magnets. Things that are not attracted to magnets, they're not ferromagnetic. Plastic, banana, mitten, sandwich, magazine. No, But how do you know? Do you go around the world sticking a magnet to every single thing one at a time?
Hey, Ma, I need you to come over. I need to see if you're ferromagnetic. No, ferromagnetic.
No, you don't need to do that. First of all, only metals are ferromagnetic. So that eliminates all your clothing, your luncheon meats, your magazines, what have you. Everything that's non-metal, you don't need to worry about.
Never mind, Ma, it doesn't matter.
But this clock is metal. It doesn't stick. Well, not all metals are ferromagnetic. Mainly just the ones with iron, nickel, or cobalt. And there you have it. Now you know your magnets.
I hit the phone on the magnet there. Okay, can you hear me, Ma? Hang up the phone. Hang up the phone, Ma.
My first attempt at levitating had the magnets sliding all over. So the plan is to take the bottom magnet and attach it to a big wooden board so it won't go anywhere. Then attach another plank to the top magnet to make it a little easier to stand on.
Okay, is definitely attached to the floor. Thank you. All right, now, if I just get this lined up. Whoa, look at that. You could totally, oh, wait a minute. Totally. It doesn't want to stay put. Oh, wait a minute. They levitate. Come on. Levitate. Why doesn't it want to stay? It just doesn't. Should I stand on it? Okay, I'll stand on it. Here we go. And. Am I levitating?
No.
No. So why isn't this working?
Well, just like your pencil experiment, we need a shaft through the center to hold the magnets in position.
Oh, yeah, maybe we could use like a ring magnet.
Yes.
That like we used with the pencil.
Right.
And
we're gonna need stronger magnets.
We're gonna need stronger magnets. Are the ring magnets strong?
Yes, they can be.
Awesome. All right, let's do it.
All right.
Now it's time for a Science Max quiz. Which one of these things do we have magnetism to thank for? Birds flying south in the winter, music, or a sandwich? If you picked A, you're right. Some birds migrate in the spring and fall using the Earth's magnetic field. Many animals can sense the Earth's magnetic field and use it to navigate. Migrating birds fly hundreds or thousands of kilometers north or south when they migrate in the spring and fall. A compass works the same way, by using magnetism to point to the Earth's magnetic North Pole. But if you picked B, music, you're right! Here's some music. The way you're hearing this music is because the musicians recorded their instruments using microphones, which use magnets. And then the signal was translated by a computer and stored on its hard drive, which uses magnets. Then it was broadcast to your TV and comes out your speakers, which use, you guessed it, magnets. And for those of you who said you have magnetism to thank for your sandwich, well, you're right. You see, you'd probably go to the kitchen to make that sandwich, right? Well, I'm guessing you got all of the tasty ingredients from your refrigerator? Well, it works on electricity, which is produced by magnets. And then there's an electric motor in the fridge that circulates the air and keeps it cool. And guess what? Magnets. And finally, the door on your fridge stays closed because the door has magnets. So there you go. You can thank magnetism for birds flying south, music, and your sandwich. It just goes to show, when you're talking about magnets, everybody wins because magnets are everywhere. This has been a Science Max quiz.
Here's an experiment you can do with a bag of water. Take a sharpened pencil and carefully push it through the bag. If you do it carefully, it won't spill. The reason this works is because the bag is made of polymers, long stretchy chains of molecules, and also because the pressure of the water against the pencil prevents any water from spilling out. Now, we're gonna max it out.
this is a very large bag of water, and here I have some very large pencils. You ready? Oh. That's one. That's two. Here we go. Should I go from the bottom? Ta-da! Science! Okay. I know what you want. Like I was saying, science! Turns out, trying to balance two repelling magnets on top of each other is pretty much impossible. Here's why. This is a magnet, and here is the magnetic field. It's often drawn with lines like this, but actually the magnetic field radiates out in all directions. Really, think of the magnetic field kind of like a ball. When you try to balance another magnet on top of the first magnet, it's about as hard as balancing one ball on top of another ball. So here's the plan. Just like the levitating pencil, we're going to use ring magnets because we can put a shaft through the center of one ring, then drop another ring magnet on the shaft. It will keep them perfectly aligned. Then it's just a matter of putting the bottom magnet on a board to keep it stable and using another board so I can stand on it, and ta-da! Magnetic levitation! Or at least that's the plan.
Okay. Board.
Magnets.
Magnets. Ooh, look at that. Awesome. And now I'm gonna put the platform on. Nice. I got some weights here. Let's see how this works. Yeah. This is gonna work amazing. All right, think I should try it?
Give it a try.
Okay. Here we go. Yeah! I'm doing it! I'm levitating! What?
Just a little bit.
Oh, really?
Yeah.
So, yeah, what do we do?
We need more power.
More power? I like that idea. How do we give it more power?
More shafts, more magnets.
Okay, sure. Well, why don't we do 1, 2, 3, 4 shafts, and then we'll have magnets on all the shafts.
Great idea.
All right. Let's do it. If you attach something ferromagnetic like this washer to a magnet, not only does it stick, but the magnetic field travels down the metal, making it a magnet too, which means you can stick more and more things to each other, and they will continue to stick until you run out of magnetic field. You can do this yourself at home with anything ferromagnetic. Paper clips work pretty well, or washers like I have, or screws or bolts, and they'll continue to stick to each other as long as the magnetic field is strong enough. You can see it's getting pretty weak here, and they'll all stay magnetized as long as the first one is still attached to the magnet. But if you want to go even further, all you need to do is keep adding more magnets to reinforce the magnetic field. I've got a few here like this. Get the chain started like that. And then I've got a magnet attached to this washer, so it will keep the magnetic field strong. And I continue to add one magnet, one washer, and we'll just see how far I can go. You can even sculpt it a little bit. Look at that. And then at the end, a whole bunch of paper clips. Eventually, the weight will make it fall off, but it's a lot of fun to play with magnets and make art. Speaking of art you can make with magnets, you can also make sculptures. When everything sticks to everything else, you can make some pretty fancy designs. This is a rare earth magnet, a very strong one, and a bunch of nuts that I've gotten. And this one here is an electromagnet, but electromagnets are a little different because they need an electric current to work. Check this out. This is sort of a magnet dude with crazy hair. There's an earth magnet here, and this is a giant screw, and these are some metal bits, and then I've got 2 more magnets at the top here to hold on his crazy wire hair. He's got crazy wire hair because he's crazy magnet dude. Now, of course, we couldn't just talk about magnetic sculptures without maxing it out, so let's max it out. This is a bunch of scrap metal from leftover experiments, and I've got a bunch of rare earth magnets, and now I'm gonna max out a magnet sculpture. Let's see. There you go, a maxed out magnet, me! I made this guy out of metal pipes with earth magnets in between, and these are his arms attached, of course, with magnets. His hand, his little metal pieces attached with magnet. Steel wool for the hair, and of course, hat, non-magnetic. All right, here we go, ready? Want to see a magic trick? Simple copper tube. Drop things through it. Nothing unusual happens, but watch when I drop a magnet through. What? It's not magic, it's science. Because the magnet creates a magnetic field, when it goes through the tube, the magnetic field repels the magnet upwards. Now, the field isn't perfect, so the magnet doesn't come to a stop, but still, it slows down from a fall to a nice, graceful drop. Take a look from above. Pretty amazing, right? Magnets, not magic, science.
So I've managed to levitate on some magnets, but just barely. What Matt and I needed was more power. So instead of having 1 shaft and 1 pair of ring magnets, we're going to use a larger board and put a shaft on each corner. Then we'll have 4 times the power because we're using 4 times the magnets. Hopefully this will be strong enough to get me floating on a cushion of magnetic energy.
And magnets?
Magnets.
Okay, here we go. This is gonna work great. And top board. Ooh, what do you think?
Looks great.
Yeah. Okay, here we go. Matt?
You're levitating.
I'm levitating! Woohoo! All right. It feels cool. It sort of feels like surfing a little bit. All right, thank you so much, Matt. That was amazing. And there you have it. Science Max, experiments at large, magnetic levitation. You know, I'm surprised we could do an entire episode on magnets, and we never actually got them so close to the camera that the camera went all weird, because cameras and magnets, they don't, oh dear, no, that's okay. I can fix this. If I just maybe, maybe if I put the magnet to the camera again, that would, okay, that's not, that didn't help. Oh, okay, well, thanks very much for watching Science Max, Experiments at Large, and we'll see you again as soon as we get a new camera.